Hello and welcome to the mini test solving to the lecture 28 mini test, the application of integrals. Here is the mini test for those of you who are here to solve it. And without further ado, let's get ahead into solving. For the first one, this is our problem. We need to find the area between these two functions, so let's identify where they're intersecting. We do that by equaling them. And then first thing we see that if x is 0, both sides are 0, so that's our first x. Now that we have the 0 out of the equation, we can cancel out the x's on both sides, and because we cannot divide by 0. But now that we know that the second x is not 0, we can. So we divide by that and we get x is 1. So our second x will be 1. This means that our interval is between 0 and 1. So this is the interval for the area. Now we need to find a value between them to evaluate which one is higher and which one is lower. I'll take something like 0.5 and insert into each. If I insert it into f of x, we get 0.25. If I insert in g of x, the linear one, I get 0.5. We see that the linear one is above the quadratic one, or the square one, in this example, in this interval. So let's set the formula. Since g is above, it's going to be first. And then we set the limits, and we put them on top and bottom. Now we just replace these functions with their functions, with the descriptions, and we basically integrate. And I just combine them because, well, you can combine them in the same integral because the limits are the same. So x minus x squared, we increase the power by 1, we get x squared. Then we have to divide by the new power that's divided by 2, minus x squared becomes x cubed, and then we divide by 3 because that's the new power. And then we set the limits of 0 to 1 or 1 down to 0. We basically double this and insert 1 into the first brackets and then the 0 in the second. Since 0 minus 0 is 0, doesn't contribute in any way, we can simply remove it. And we're left with 1/2 minus 1/3, which a simple fraction difference between fractions, which we know how to solve. We expand the fractions into sixth common denominator. 3 minus 2 is 1, so 1/6 is the answer. So 1/6 of a square unit is the answer of the area between the two functions. That's it. For the second one, we pretty much do the same thing, as the only thing changing is the slope of g of x. Here we can see if changing one function to be just 2 times x is significantly gonna change the answer. Because on the first note, you would look at this and be like, oh, this can become 2/6 or 1/3, but let's see. So we're doing the same thing, equal the functions. The first x is 0, the second one is 2. We set our interval and determine which one is above and which one is under. We insert 1, which is in the center. We get that f of x gives us 1, g of x gives us 2, so g of x is above, so it's going to be first again. Between 0 and 2, we insert the functions into the formula. We integrate, we get x squared halves, but since it's 2 times x squared halves, 2's cancel out and it's just x squared. And then we subtract x cubed thirds. And then between the 0 and 2 limits, we insert the 2's only because if we insert zeros, nothing changes. We saw that before. So it's 4 minus 8/3. Now we expand to the common denominator, and we're left with 4/3, which is a whole 1 more than we would expect. So the surface is 4/3, and we see that it's not just linearly increasing. You can find the correlation between the surface and changing of each of the functions if you want. It's a fun thing to think about, so yeah. As for the third problem, here it's slightly different. We have an absolute value which slightly changes things, but not much. First, we need to determine what the values of f of x even are. As we know, absolute values change whatever is inside to be positive as the result. So let's write it out. So I had it written out in another program to allow me to ease of use of different levels, like how spaced out the rows are. Plus, it's nice to keep it on the side, so let's determine the intersections. So absolute value of x is 1. What could x be to make this equation true? Knowing the property of absolute value, we know that anything inside will end up positive, so x can be plus minus 1. So we have 2 x's, plus 1 and minus 1. We could also just equal 1 with each of these two, But I mean, that probably is the best way to go to make sure you don't make any mistakes. Now that that's that, we insert the value between them, like 0, because it's between them, into our functions, and we see that the absolute value one is lower, so g of x is the top one. So we're gonna be... This is the wrong setup, but I will correct it on the next slide. So this is the 1, and this is the absolute value of x. So yeah, I made an oopsie, don't ignore that. But yeah, this is the setup for the integral. Now we have another problem. How do we integrate absolute value if it changes its behavior, especially mid-interval? Well, let's remember the rules and what I mentioned in the video. Addition and subtraction can be broken up into two integrals, and since integrals represent the surface, if we break the integral for absolute value into two, one when the x is inside the less than 0, and the other one when it's greater than or equal to it. So this is... I just corrected from the slides to this one. But yes, if our absolute value graph looks like this, then where does it make sense to break the integral apart? And that is at x is 0, because one behavior is before that and one is after. How do we do that? We adjust the limits by just adding up two integrals, one with limit -1 to 0 and the other one to 0 to 1, as we showed in the video. And of course we can insert in the right function for the behavior of x to avoid the absolute values, like this. I'm circling minuses to make sure that we don't forget them. So we can replace this orange part with this orange part. So when the x value would be negative, so when x is less than 0, we use this writing, so minus x to become positive. And this basically determines what the value of x is. So x is less than 0, okay, we multiply it by -1 to get it positive. And when it's positive, it's positive. So I will insert this in here, and the minus will stay here, so keep in mind. So we will do the same thing to the left part and just add them together where they are in the same limits, so the same integral. Because, well, it makes sense if you know the rules. I did forget to mention it last time, but yeah. You can do that if the limits are the same. It makes sense, but you have to see it first to make it make sense, right? But yeah. So hopefully you can follow along. So I broke the other one into two integrals as well with different limits. So we can add 2 by 2 together. Be careful of the signs in front of each. So this sign goes with the purple part and this one with the orange. So we get this minus x, minus x, and this one minus x. So like this. Now, since there's two colors and two parts, and to avoid covering the graph that I saw nicely drawn, I will write out each part separately, so purple and orange, P for purple, O for orange. So I simplify this and integrate. This integrated gets to x, this gets to x squared halves within the limits of -1 to 0, and the orange part gets to x and minus x squared halves between 0 and 1. So now that's integrated. Let's insert the values. 0, 0 minus the -1 inserts, and then the 1 insert minus the 0 insert. The 0 inserts disappear. We're left with these signs. I solve inside here, it's -1/2, and here it's 1/2. Now we have -1/2, which is 1/2. As each of these two gives us 1/2 as the result of the integral, it makes sense because it is a symmetrical graph and we did break it down the middle. So this is kind of a proof we did something right. Now we just add these two together and we get this overall surface of 1. Since I kind of forgot to draw the graph, but like this is the g of x, this is the f of x, and this is the integral of 1. This is 1, -1, 1. Kind of makes sense if you're looking from a geometrical point of view, because this is like 1 times 1/2 and then 1 times 1/2. But yeah, this is it. Thank you so much for tuning in to the mini test solving. I hope everything went well. If it didn't, comment down below and join my Discord to make sure, and I'll see you all next time. Bye!